Okay, good morning. This is our last topic for the week. So, this is continuity. So, we've really kind of talked about limits. Now, we're going to switch and talk about continuity, which of course is related. You guys know that. But it's a big word. No worries. Continuous just means that you can draw the function without lifting up your pencil. So like a piece of string, if you will, and it's not cut, right? It's continuous throughout. So continuous just means there's no gaps, right? Means you can draw the function without lifting your pencil. That's how I envision it when I work with continuity, right? Okay. Now we typically talk about continuity at a point, okay? And I'm not going to write out the formal definition because I don't think it helps us that much. But continuity at a point just means that the limit exists at a point and it equals some number, right? And this is the big thing. And if I if I do the direct substitution into that function, I get the same number, L. Okay. Okay, so if we think about this graphically, right, we've got some graph, say, and a point A. Okay, and we're looking at this function here, say, this is our f of x, right? So this left side means that the limit exists, right? And so if we check for continuity, formally, if we're checking for continuity, we have to prove that the limit exists. And you guys know that because we just did like 3 lessons on limits, right? So for continuity, you have to prove that the limit exists. And you remember that's that 3 steps, right? We prove that the limit goes to A from the left, right? If we approach A from the left, we're getting L, right? So if we're going to approach A from the left, oops, dang it, sorry about that. That's not a plus, that's a minus, you guys, that's a minus. Okay, and then we're approaching L there, right? And then our second step, obviously, we're going to prove that limit exists. Now we have to come from the right side. So we're going to go towards A from the right side, along, and then we're also approaching L. Therefore, my 3 little dots, therefore, the limit exists, right? Of f of x is equal to L. So we just proved that the limit exists. Prove limit exists. Can you see that? Yeah, good. And then the last step now for continuity is we're going to add a step 4. And that step 4, we're going to actually plug in A. And that has to equal L. So here what we're doing is we're filling in that hole, right? Now we're plugging in A. Do we get L when we do that? And if we do, we filled in the hole, and this is all equal for continuity, okay? We filled in the hole. And so kind of the shortened version is if we do take the limit as x goes to a of f of x, that has to equal f at a, meaning all four of those are true. Oops, pen's going out a little bit. I have to change colors there. It sure looks like it. Okay, and this is our definition of continuity. Okay, how are they gonna test us on that? On the darn AP test, what's going to happen, right? Okay, so typically they're gonna give us some sort of piecewise, a lot of times they'll give us a piecewise function. And they'll say what value makes this continuous. So let's do, oh, that's not working either. I'm gonna have to make an essential trip to get more pens, huh? Okay, example 1. Is Office Depot even open? I'm not sure. Okay, so what value, K, makes h of x continuous? So this might be how the AP tests us. So they give us some sort of lovely okay, and that's if x does not equal k, and if x equals k, then our function is equal to 2. Okay, so now we've got to set these two equal to each other. So if we're approaching k here, that's this side of the equation, right? And if we're at k, that's this side of the equation, right? So if we say, okay, this is the left side and this is the right side, I'm going to set 1 kind of equal to 2. So we're going to say the limit as x approaches, what are we approaching? Yeah, we're approaching k here, right? As x approaches k of h of x, see that? Yeah, is equal to h at k. All right, now we just keep going. So now we're going to find the limit as x approaches k, and we're going to use the first function here, x squared minus k squared over x minus k. And that is going to have to equal h of k, which is, you got it. Oh, you can't see it. Sorry about that. H of k is, yeah, 2, right? Okay, now we've got to solve this. Excuse me. We've got to solve this limit. So it looks like a factoring to me because I see this as difference of squares, right? So x minus k times x plus k. And all over x minus k, and lo and behold, yay, the x minus k's cancel algebraically. And now when we do that direct substitution, we're not going to get the 0 over 0, the indeterminate form. Now we get k plus k is equal to 2. So 2k is equal to 2, so k has to equal, you got it, 1. So always, 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 though, remember with these, you have to start with the definition of continuity. And if you do that, you'll be okay. Okay, sometimes there are direct substitution limits. You can just set them equal to each other. But sometimes you actually have to take the limit, like in this problem. All right, guys, good luck. Thank you.